Okay, so last time we were going through System Verilog. I mentioned that System Verilog and the HDL are the two popular HDLs. You can do synthesis and simulation. HDL designs are comprised of modules that can be interconnected and instanced hierarchically. Modules have inputs and outputs that are given on the module line. And then inside the module, we can have behavioral HDL that is Boolean logic, truth tables, finite state machines. Or you can have structural HDL, which is where you instance and interconnect other modules. When you simulate, you get a waveform interface, and when you do synthesis, you can potentially get different synthesized results from the same code, as long as the synthesized design performs the behavior as given in the code. Okay, we looked at some examples and went through operations, operators, numbers, constants, bit twiddling, sometimes called bit swizzling. In this case, you can take multiple values and concatenate them together using the curly braces. And in this case, that's being done on the right-hand side of the assignment, but you can also do this on the left-hand side of the assignment, which is looks a little strange, but we have an example of that right here, where I've got these three signals, AB, BB, and CB. Each one of those are 1 bit because they're declared as logic with no bit range. And I am assigning all three of those together as if they were one 3-bit signal. Everyone see that? And so I'm taking ABC, putting those together as taking those three 1-bit values, putting them together as a 3-bit value, complementing it and assigning it to the 3 bits corresponding to AB as the most significant, BB and CB as the least significant. Everyone see that? Okay. I think this is where we left off last time. So we've got some assignment statements here with these, right after assign, you have delays listed. The delays allow you to add some delay because normally there's no delay. Normally the HDL is not tied to a particular technology. So there's no propagation delay associated with it. Propagation delay is something that's associated with a target technology device, right? Like an ASIC or an FPGA. But normally with HDL normally it's just behavioral. There's no delay, and so you don't see any delay. If you want to add delay, you can actually add it by putting explicit delays in. And in the case of assignment statements, you can put it in right after the assign. So let's test this out. How would you do something like this? I'm going to connect here. Hopefully this works. We have a commercial simulator called Model Sim installed on all the lab machines in the department. So now I mentioned there's some free ones too. There's I think the only free one that I know of that works with System Verilog is called Verilator. But we don't have Verilator installed on all the lab machines. You'd have to, you could install that on your own Linux machine. If you're on a lab machine, so I'm going to connect here to L-1D43-01-.csce.scivu. That's one of the lab machines in 1D43. Oh, sorry, port 222. I'm going to do Duo because I'm on Wi-Fi. You guys all have Duo set up? And it didn't work. Okay. Well, there you go. Oh, there it is. Now it's working. Third time's the charm. Okay. So I'm going to source the script required to set up this tool, which is in user, local, third-party, CAD setup files, altera.bash. You don't have to necessarily know how to do this, because, but I just want to demonstrate how HDL, how you can simulate HDL. I'll create a directory here called foo. Oh, already got that. Foo2. Yes, there we go. Foo2, and then I will create example.System Verilog. So I'm just going to go over here to the slide, and I'm going to copy this and paste it in there. And there's my file, example.sv. So the first thing normally, whenever you want to simulate an HDL, you have to compile the HDL, the description, the design, into some form that can be simulated. So in the case of model sim, it's vlog, which stands for Verilog compile, example.sv, and that compiled it. So it found top-level module example, 0 errors, 0 warnings. And then I can simulate it by typing vsim example and then no vopt. Hello, come on. Come on, video. There we go. Okay, so there we go. And this is model sim, a little compressed because of the resolution being lower here. But over here I've got all the objects, and so I'm going to add them. So here is A, B, C, Y. Those are the top level inputs and outputs of the example module. And then I've got A, B, 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 C, B, N1, N2, N3. I forget what those what were those all about? Oh, those were just, yeah, those were just, I don't know why they named them the way they did, but we have internal signals A, B, 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 C, B, and N1, N2, N3. So those are the 6 internal signals. And then A, B, C, and Y are the top level IOs, right? Okay, so we don't need a clock. This is purely combinational logic. So there's no clock. But I do have to do something with the top level IOs because there's nothing driving A, B, and C. A, B, and C are our top level inputs, but the idea is that somebody would instantiate example and then be driving, setting those inputs. There's no one to do that because I'm just simulating the example by itself without some sort of test harness, test bench to set those. So I'm going to have to do it. So here in Model Sim, I can do a right click on A and I can just say force. I can force this to be a 0. And then B, I can say I can force that to be a 0. I think that's what they are in the on the slide. And I can force C to be a 0. Okay, and then I can run the simulation by hitting the run button up here. And I'll hit it a few times. And then I'm going to zoom in at the beginning because I was zoomed out so far I wasn't able to see the very subtle differences here. So you can see that at 0 nanoseconds, if you look at the x-axis, the 0 nanoseconds, all of the units that I had after the hash marks were in nanoseconds, only because Model Sim was set up by default to use nanoseconds as the time scale. So A, B, and C get driven to 0 at the beginning because I forced them to 0 before I ran the simulation at all. So the simulation was at time 0. I set A, B, and C, so they get set at time 0. And notice that A, B starts out as X. So it says X here because that's where my cursor is at 0, AB is an X, which means undefined. Because it's not defined in the design before it was set, and it wasn't set until that one time unit after one of its inputs were set, which was, let's see, AB depended on what? AB depended on A, B, and C. So A, B, and C were set at time 0, and then I was going to update AB, BB, and CB at one time unit after that. So prior to that, it was undefined. Everyone see that? So AB, BB, and CB are all updated here at 1, and then I come over here to N1, N2, N3, and they don't get updated until 3 nanoseconds because those depend on, well, this is a little complicated. So N1 depends on AB, BB, and CB. Those are undefined until 1 nanosecond, and then I'm going to at which point I'm going to activate this line, but I'm not going to update N1 until 2 time units later. So N1 won't be updated until time unit 3 nanoseconds. Everyone see that? Okay. And then N2 is a little bit more complicated, though, because N2 depends on, when I say depends on, I mean it's sensitive to inputs A, BB, and CB. And when I say inputs, by the way, I mean, signals that appear on the right-hand side of the assignment statement. Now, A was set at time 0, and BB was set at time 1, but at time 0, I would have one value there, A, which is defined, but the other two are not defined. So if I take a value that's defined, like a 1, and I do an AND with an undefined, I'm still going to get an undefined. You guys with me? So as a result, I'm not going to see anything on N2 until the same time as N1, right? Yes?
So since you already know that A is 0, does that make it to where it would already know that the information is going to be 0?
That's a good point. Yeah, it's a good point because it's an AND. Yeah, anything ANDed with 0 will be 0. But apparently, that's not how ModelSim did it, because if that were the case, N2 would have been known at the same time that A was known, right? So I never noticed this before, but you're right. If even though you would think that it wouldn't matter what those other inputs were if I'm ANDing with A, it still waited until all the inputs were defined. So in System Verilog, if you have an AND and you AND with if you have an undefined value in that AND expression, the whole expression is evaluated to undefined, even if another one of the inputs was a 0, right? Okay, and then Y was way out here at 7. Y didn't get set until 7 nanoseconds, and that was because we had to wait for 1 to get. Well, let's see. Y has a delay of 4 with respect to N1, N2, and N3, which was delayed for 3. So the total delay of Y was 7. Yes?
So the hashtag 2 is the nanoseconds, the delay?
It's nanoseconds now because when I started ModelSim, by default, it uses nanoseconds as the time unit. I can change that, though. What's that?
It can be any time unit.
Well, you can set it in the simulator. I don't remember where it's set. I think it's under. Actually, it's right. It's in the settings here somewhere. Maybe under simulate. When you go to start simulation, does it resolution? Yeah, you can change the resolution here when you start the simulation. But if you care about that, it's easier to just do it in the Verilog, in the System Verilog. And so to do that, I'm going to edit example.sv, and if you put backtick time, what is it now? Time spec, 1 picosecond. 1 picosecond. Is it time spec? Time scale. Sorry, time scale. Time scale. There we go. Okay, so now I'm going to vlog example.sv again, and I recompiled that. Then I'll go back to ModelSim, and I'm just going to restart. And I wonder if this will, let's see, I'm going to say force A to 0, force B to 0, force C to 0. See, you can just type those commands in here, and then I can run this guy. And now I ran it for 100 nanoseconds, but if I zoom in to the very beginning, let's see, zoom, 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 zoom. Yep, well this is, yeah. So notice the time scale is different now. It's 0.002 nanoseconds, meaning that that's a picosecond now. So it did change. It updated the scale. Okay, any questions about that?
But from a coding perspective, the hashtag is just the time delay. It can be anything.
Yes, well, if you were using that for modeling delay, like if you synthesize your design and then the synthesizer would go back to your HDL and annotate delays into it, then it would set the time spec and then it would set the delays according to the time spec. Okay. Okay, so I showed all this stuff in the simulator. Okay, so you might be wondering now, how much can you do with an always statement? Well, not too much. Pretty much just Boolean logic. If you want to do something more complex, including any sequential logic at all, you have to use something called an always statement. Now, it's called an always statement, but generally always statements contain a block of code comprised of multiple statements, which you can do by putting a begin and an end. So if there's more than one, let me back up here. So an always statement, it allows you to create a complex concurrent assignment statement. It has this thing called a sensitivity list. So you start out by saying always at and then sensitivity list in parentheses. Sensitivity list is the list of signals that you want the always statement to be triggered by whenever they change. So this is equivalent to, in a concurrent assignment statement, anytime any of the signals on the right-hand side of the assignment change, it will trigger this always statement. And in this case, it'll trigger it, and then it'll actually update the output after the delay. In an always statement, an always statement is going to hold all of the outputs that it sets inside the always statement will be held until something in the sensitivity list changes. So what is this useful for? Well, for one, it's useful for sequential logic. You can imagine what would go in the sensitivity list. It would be the clock, right? So if you have an always block, always statement containing a block of code, and inside that block you can implement sequential logic, and then the sensitivity list would have the clock, and anytime the clock changes state, it will activate that always statement and update the outputs. You guys with me? The other thing you could do with an always statement is you can use slightly more complex constructs in there, like if statements and case statements in particular. Okay? So by the way, in Verilog, you just have an always statement. And if you're using an always statement to create sequential logic, you put the clock and possibly the reset in the sensitivity list. If you're using an always statement to do combinational logic with an if statement or a case, as opposed to just using a concurrent assignment statement, then you have to put everything in that sensitivity list that would serve as a potential input to the combinational logic. But what happens if you forget one? Well, then it causes problems. So it's an issue that they solved in System Verilog by introducing a couple different varieties of always statements that you can use optionally. So the first one is always underscore FF, which means flip-flop. So this is what you would use whenever you want to make an edge-triggered sequential logic block. So in that case, you say always at FF, and then inside the sensitivity list, you would just say posedge clock. This is rising edge of clock. Everyone with me? Make sense? Now, what is the purpose of this always underscore FF as compared to just saying always? If you make a mistake in your code and you put something in there that is not edge-triggered sequential logic, it will give you a warning when you compile or synthesize it. That's the idea. Okay? So this thing is a flip-flop. This is implementing a flip-flop. It's saying always at posedge clock, and then inside the always statement, it's assigning Q gets D, assigning D to Q. Now notice that the assignment looks different. It looks like an arrow here. And I'll talk about that more in just a minute here. Also notice that D and Q are 4 bits, so this is a 4-bit register. Everyone with me? So we can we can try this out pretty easily. I'm going to take this code. I'm going to copy it. A copy. Go down to my shell. I'm going to create flop.System Verilog. Then I'm going to paste that in. And then I'm going to say vlog flop.System Verilog. No errors. And I'm going to say vsim no vopt flop. Oh, I should have used the one I already had open. That's all right. OK, so this opened a second model sim window. And I've got my flop here. And I'm going to select all the signals that are inside there. I'm going to say add to wave. That'll add them to the waveform viewer. Eventually, there they are. And so now I want to take clock, and I'll do a right click, and I'll go down here to clock, and this brings up a window. It says duty cycle 50, period 100. So this will create a clock with a period of 100 and a duty cycle of 50, and hit OK. And now, if I run that, I'll hit run a few times. I get a clock. See that? I got my clock, and it's using a period of 100 nanoseconds. You can see that because there's 400 nanoseconds, 800, so that's 4, 5, 6, 7, 8. And it's 50% duty cycle means it's high for half the time and low for half the time. But D is a Z, 4 bits of Z, meaning high impedance, because I haven't set it. And so is Q. So if I want to, I can set D now, and I can capture that in my flip-flop. Now notice that at this moment in time, the clock happens to be rising at where the simulator currently sits. So if I were to force, maximize this. If I were to force D to be 4 apostrophe B, binary, 1010, and then run. OK, so that's where I forced it. I forced it when the simulator was at, let's see, what is that? 1,000, 1,500. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's what, 50? Yeah, 50 per division. Right, yeah, that makes sense. So this was at 1,100, right? So at 1,100 nanoseconds, the simulator was stopped. I forced D to be A in hex. See how it says A, 1010 in binary. And that happened right on the rising edge of the clock. But at that point, it was too late. I got to wait to the next rising edge of the clock for that value to get captured into Q inside the flip-flop. And you can just about see that starting to happen there. But in order to really see it happen, I got to run it again. Oh, there it is. So there's where the value got captured into Q. Everyone see that? So this flip-flop created this 1 cycle delay from when I set D to when it was captured into Q. Sound good? I could change A, by the way, to B, which is 11 in decimal, or 1011 in binary. I'll run it again. And so here's D is changed there. But Q hasn't updated until one cycle later. So there's the B gets captured in there. So this is the way you make flip-flops or registers in Verilog. The book calls this an idiom. And what that means is that if you want to guarantee that the synthesizer will implement this code as a flip-flop in whatever your target technology is, you should write it exactly in this style. This is how you should make a flip-flop, a register. There are possibly other ways to do it in valid Verilog, but if you do it that way, you stand the chance of the synthesizer not understanding what you want. So when I wrote this, I was thinking I want to put a flip-flop, and so I wrote it in this style to achieve that. Okay, so it's kind of like a template almost. You can add some features to it though, like if you want to create a synchronous reset, you could have a reset signal come in, and inside the always block, you can put an if statement in there. Now this is a new syntax, by the way, you haven't seen before, an if statement, or at least in System Verilog. You cannot put an if statement outside of an always block. You can only put it inside an always block. Always block, by putting code in an always block, you unlock the capability to use if statements and case statements. And by the way, VHDL has exactly the same rules, except in VHDL this is called a process. In Verilog it's an always statement. So in this case I say if reset is asserted, I want to reset, otherwise I want to do what I normally do by capturing D into Q. But because I don't have reset inside the sensitivity list, this automatically becomes a synchronous reset. So if I try to reset this thing, nothing will happen. If I try to reset this by asserting reset, nothing will happen until I get the next rising edge of the clock. You guys with me? So I can give that a shot. Let's see. Flop. I will modify this and say if reset, then Q gets 4'B0, 4 bits, right? Yep. Else that. Now I didn't put a begin and end statement here because an if statement just counts as one statement. But just to demonstrate that, I'm going to go ahead and put a begin here and an end here. So this is kind of like in Java. If you just have one statement in a basic block, you don't need the curly braces. I didn't need the begin and end here, but I'm going to put it in just to demonstrate that. The book didn't put it in because an if statement is just one statement. And then I need to add my reset. Well, I don't need to add it. I could make it an internal signal, but since I'm driving it anyway explicitly. But I'm going to make it an input logic reset. Okay, save. Then I'm going to go back to model sim, and I think if I go to, can I say recompile? Or no, it's actually under library. If I go to library, I go to flop, I can say recompile. I can recompile it within the GUI, and then I just need to restart it with that button, and then I can run it with that button. Oh, I need to bring in my reset, by the way. And since I didn't bring the reset into the waveform until 400 nanoseconds, the wave actually doesn't show up until 400 nanoseconds because it wasn't recording that, but that's fine. I don't care. And now I can say force, reset to 1, run, and reset goes high, and nothing happened. Oh, because I don't have a clock either. I need a clock. Sorry, I forgot to reset my clock. So let's set up the clock. So the clock, and again, because I didn't do this, I didn't set up the clock until about 800. Where are we at? Oh, yeah, it says down here, 800 nanoseconds. I didn't set up the clock until 800 nanoseconds. It's not going to appear until 800 nanoseconds. So that's where the clock is going to start going. Up until then, it's just a Z, high impedance. It's not driven. And then, but my Q got reset right there because when I started the clock up, the first edge of the clock was a rising edge. And so it triggered off of that first rising edge. And I don't know if you noticed that, but when I set up the clock, you actually say that right there. It says the first edge rising. So when I set this up, the first edge was rising, and thus, because reset was already high at that time, that was when it reset it to 0. Any questions? Okay, hopefully this is how, usually when I cover, this is the first time I've actually ran these examples as I was presenting them. Usually I just blow through these slides, but I think this might make it a little, I think this might make it clearer what's going on by running these in real time here. Okay, so that's a resettable flip-flop. And if you want the reset to be asynchronous, you can add it to the sensitivity list by just putting a comma and say posedge reset. So now, if the reset ever rises, it will reset that flip-flop immediately. And then finally, as a final feature I can also add an enable, which, and we talked about this in chapter 3 a little bit. Some flip-flops will have an enable that if the enable is not asserted, it will ignore the clock. So if you have, like in the MIPS processor, you've got a high and low register, for instance, that only get updated when you do a multiply, when you execute a multiply instruction. That's an example of that. So in this case, I say if reset, reset, else if enable is asserted, update Q to D. Now, Q does not get set on every control path through this if statement. And in general, if you ever have any always block that doesn't assert all of its outputs anytime it's activated, that will imply memory. So if you accidentally build, well, in fact, I think we have an example of that, as a matter of fact. Yeah, here's an example. Well, actually, what I was about to say is if you accidentally forget to assign something when you meant to, it could create a latch. But this is, in this case, we're explicitly going to create a latch. And there's a special always for that called always underscore latch. In this case, if you say always underscore latch, you can create a latch explicitly by saying if clock is asserted, then pass Q over to D. So this would create a level sensitive latch. In general, you don't want to, it's not a good idea to create latches. The book authors say we don't use latches in this text, but you might want to write code that inadvertently implies a latch. You check your synthesized hardware if there's latches in the synthesized hardware, which you would know because it generates warnings usually when you synthesize your code. If there's a latch, you should get rid of them. Okay, and then I mentioned that in an always block you can use if statements. You can also use case statements. Oh, actually, sorry. This is for sorry. Let me skip ahead. Actually, yeah. So here's an example of a case statement. In this case, notice I'm using an always underscore com. So I've showed you 3 varieties, well, actually 4 varieties of the always statement so far. Let me back up here just to make this clear. So if you can just say always, which is how we've always done it in Verilog. System Verilog introduced the always underscore FF, which is just an always statement, but it tells the synthesizer that you're trying to create a flip-flop. And so if you screw something up in the code that would prevent it from behaving as a flip-flop should, you'll get a warning. So always underscore flip-flop, and then in this case, it's looking for, I think if you put anything in here that's not posedge something or negedge something, it'll give you that warning. You guys with me? So this is always underscore FF is for flip-flops. Then there's an always underscore latch, which the book and I recommend that you don't use, but it's in there anyway. And then you can finally, the last form is an always underscore comb. In this case, you don't have a sensitivity list because it's implied that anything that's treated as an input would be in that sensitivity list. Anything inside the always block that's treated as an input. So in this case, I'm assigning y1, y2, y3, y4, and y5. I've got 5 outputs, and they're just simple assignments. So everything on the right-hand side of each one of those 5 assignments is being treated like an input, and thus is considered part of the sensitivity list. So you can think of this as putting 5 concurrent assign statements together, or I can combine them all together inside this one always block. You guys with me? If you have an if statement or a case statement, which, let me show you a case statement. So here's an example of a case statement. The case is switching on the data input, which is a 4-bit input coming in here. That would also be treated as an input, and thus would be assumed to be part of the sensitivity list. So if data were to change, it would activate this always, and it would evaluate the case statement. Everyone with me? In the previous example I showed you, if A or B changes, those are treated as inputs inside the always statement, so they'll cause this always statement to trigger, and it'll evaluate that if statement and update y1 through y5. Everyone with me? So to kind of summarize, if you have always at comb, the sensitivity list is implied to contain anything on the right-hand side of an assignment statement, or anything that you're switching on in a case statement, or any expressions, any conditional expressions that are in an if statement. Those all would be considered inputs. You guys with me? Okay. So always comb, always latch, always flip-flop, and then there's just the always. Now this is, by the way, this is new for me. I've never used one of these always comb, because this is the first time I've taught this course with System Verilog. But with regular Verilog, if you're doing combinational logic, you would say always at star. You would just put a star in here. So what that means is that the always underscore the comb is just a shorthand way of saying always at star. Let me write that down so it's clear. So with regular Verilog, which is what we used up until this semester in this class, you would say always at star if I wanted to create combinational logic. Now you might say, wait a second, you could do combinational logic with an assign statement. Yeah, but you have to use the trinary operator, and if you want to do complex combinational logic, you should use an always at star. Sorry, always at star. Forgot the at sign. Always at star, right? And then you could say begin. Notice there's a begin. Oops, sorry. Notice that there was a begin and end there, right? There should have been at least. Yeah, see, begin and end right there, because I had more than one statement in that always block. Begin and end. System Verilog created this new one called always underscore comb, in which case I don't need the at star. I can just say always comb, and it just implies it's the same thing as that. Begin, end. So these two are equivalent. Okay? It's just a new System Verilog way of coding. This case statement, by the way, is a 7-segment decoder, which you guys, I think you designed one of these in 211 using the TTL chips. This is how you do it in Verilog. You would have the easiest way is you could use an if statement, but this kind of lends itself to a case statement. You case data. Data is the 4-bit hex character, actually decimal in this case because it only goes 0 to 9. So data is a 4-bit decimal number, 0 to 9, in binary, but decimal because it's only 0 to 9. And then segments is the 7-bit output that goes to the 7-segment display. And then, so then it kind of follows, it's kind of like Java, although Java would say switch here, but this says case data and then If the data is 0, then I would set the segments accordingly. Notice that there's no break. There's no break statement here. That's kind of different from Java and C. You don't have to put a break statement. There is a default statement that you should have. Actually, they say required. It might say require. It might give you an error if you don't have the default. Now, one thing the book did that the book authors actually screwed up. They broke a rule here with this. Notice that this 0 and this 1 and this 2 are constants, but as I said in the last lecture, whenever you have a constant, you should specify the width of the constant. So this should say for apostrophe D or H, doesn't matter, 0. You guys with me? I say it doesn't matter because it's only 0 to 9, so there's no difference between decimal and hex until you get past 9. Everyone with me? So the book, this is bad form to not put the size there. Any questions about that? Okay. Now there is a nice variation on the case statement where you can use this case Z, where you can also put in don't cares. So if you use a case Z statement, you can have some of the bits. Notice that they put the size there, by the way, for apostrophe. So this says case Z A. A is the input here, 4 bits. And in this case, they're now saying 4 apostrophe B. And then they say 1 question mark, question mark, question mark, which this one line would expand to 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, and so on, right? You guys with me? So it's kind of like a wild card saying that I don't care what the value of the least significant 3 bits are. Of course, notice that it's kind of strange because you get to the next line. Oh, yes, it starts with 0 there. That's why. Yeah, I was going to say. Yeah, if you had a 1 there on that first digit on the next line, it would get ignored because it would be consumed by the first one, but they have a leading 0 there. Any questions about this? Okay. Okay, so now we're getting to what I think is one of the most confusing parts of Verilog. You might have noticed that when I had always underscore flip-flop, I used this assignment statement that looks like an arrow. It looks like a less than equal sign, but it's designed to look like an arrow, right? But when I showed you the combinational logic, always at comb, notice that it used a regular equal sign. Why is that? Well, that's a very subtle but very important distinction. And it's kind of hard to explain. The arrow-looking assignment is called a non-blocking, and the regular equal sign is a blocking assignment. In general, you should always use a non-blocking whenever you use a sequential logic block, and you should always use blocking whenever you do combinational logic. And normally, if you follow that rule, everything will be fine and you don't have to worry about it if you follow that convention. The difference is, though, that if you use non-blocking, when the always statement activates and is evaluated because one of its sensitivity list signals gets changed, whenever you assign something with a blocking assignment, if you refer to that signal that you assigned on a line inside the always statement below it, it will see the old value. Okay, so you got to think back here for a minute. Think about, I mentioned at the beginning of this chapter that Verilog has concurrent semantics, meaning that every line of code, you could think of every line of code as executed concurrently because every line of code, or rather every statement, actually I should say is more accurate, every statement in Verilog is executed concurrently. They're all running at the same time. There's no notion of a current line or a program counter, right? And the reason for that is because every statement in Verilog is intended to be a circuit, and circuits work concurrently. Circuits are all acting, constantly acting, right? There's no, it's not like you have a chip and there's some sort of ordering to the way that circuits propagate their signals, right? Now, in an always statement, things get a little strange because an always statement or a block of code that you have in an always statement between the begin and end, it sort of looks sequential. It sort of looks like Java or C because you can have things like case statements in which the order of lines in the case statement does matter. If statements, the order of lines in an if statement, you think of that as being executed sequentially. But there's this subtle thing that if you assign something inside an always block, inside of an always block, and then you refer to that signal after that assignment, it will see the old version of the signal, meaning that they still enforce the ordering doesn't matter idea, even inside an always block, if you're using non-blocking assignments. What ends up happening is that the always block gets evaluated, but none of the signals that you assign get immediately updated, not until everything's done, not until the whole always statement has been evaluated. Does that make sense? Right? So in this case, in this example that they have, you say always at flip-flop pause edge clock. The clock edge occurs, the always statement gets activated, and it writes N1 inside here. It updates N1. Then in the very next line of code, it uses N1 to assign to Q. Right? But when it does that, it doesn't, the second statement does not see the updated N1. It sees the old N1, not the new N1, right? So this statement ends up becoming synthesized as two flip-flops connected in series, meaning that whenever this updates, I'm going to put D into N1, and then I am going to put into Q, I'm not going to put what's in D, but I'm going to put what was previously in N1. Which means that this guy is going to create a 2-cycle delay between D and Q. It's going to take 2 cycles to propagate a signal from D to Q because it's going to take 1 cycle to get D into N1 and a second cycle to get N1 into Q. So there would be a 2-cycle delay. Which doesn't make sense when you look at the code because in the code there's this data dependency that says that, oh, well, I set N1 on the first line and then I use N1 on the second line. But when you use it, it's seeing the old value, not the new value. Any changes you make in an always statement are not actually, they don't take effect until the always statement is done. Does that make sense? You guys follow that? Yes?
To be clear, the one that has the 2-cycle delay is the one on the right that uses the blocking assignments, right?
No, the non-blocking is that's the other thing that's kind of weird. The terminology is strange. They call it non-blocking, right? I don't actually know where that comes from, but the name non-blocking. But what it means is you don't update anything you update doesn't take effect until after the always statement finishes, right? In this other case, in this other one, we use blocking assignments, right? In this case, in a blocking assignment, I'm going to put D into N1, and then the next line of code will see the new N1. So this always statement is actually redundant because this gets evaluated to just one flip-flop, right? Because basically, because D is going in N1 and N1 goes into Q, this is equivalent to just taking D and putting it into Q, right? Right? Because it's a blocking, right? Does that make sense? And so that's pretty confusing, but to make it even more confusing, it gets even worse. It turns out that, and I learned this the hard way, it turns out that it's not even limited to a single always statement because you might assign something in here. You might assign a signal in an always statement that's used in another always statement. In fact, that's pretty common, right? But if you do that with a blocking assignment statement, and if both always statements are activated on the same edge, then it's equivalent to putting everything in the same always statement. guys with me on this? So this is what I screwed up on when I was generating a waveform for the exam 2. I used a blocking assignment statement when I was generating the inputs to the state machine example that I had or the state machine problem that I had on the exam, which is what caused the issue. But I'll get to that. I'll come back to that in a minute, because in order for me to describe that, I have to get to the initial block, which is in a slide coming up. But in terms of, if this is confusing to you, you should if you just remember to always use this for sequential and this blocking for combinational, it should be fine, right? That's a good rule to go by. You won't run into any problems. Okay. Okay. So this slide summarizes always statements and what they're all about and what you use them for. Anytime you need sequential logic, use an always flip-flop at posedge clock. And optionally, you can add a comma posedge reset if you want an asynchronous reset. Right? Also use non-blocking assignment. Right? Simple combinational logic, like if you want to do something simple like a little mux here or there, right, or a little Boolean statement, use a concurrent assignment statement, which is where you put assign space output equals expression. Optionally, you can use the trinary operator to add decision logic in here, conditional execution. You with me? If you want to do more complicated combinational logic, a good example of that is that 7-segment decoder that I showed you. A 7-segment decoder is a little bit too much for an always statement. You could do it in an always statement, but it would look, wouldn't be very readable. Then use an always comb and with blocking assignments. Okay? And finally, the last bullet here is also very important. In an always statement, if you assign a signal, you cannot assign that same signal in another always statement or in one of these assign statements, or with another module that you instantiate, because that'll double drive it, right? What does that mean? What do I mean by it? What I mean by that is that you can think of an always statement as a circuit. And anything it assigns, it's that circuit is assigning it. Now you can assign the same value multiple times in one assignment statement, that's fine. But don't assign the same value in multiple assignment statements, or you're going to see in the simulator it'll show an X there, meaning that it's double driven. It means that you've got two circuits trying to set the same voltage, the same bit. And if you go to try to synthesize it, the synthesizer won't let you, because if it did, it would allow you to synthesize a circuit that would be damaged if you actually operated it. Okay? Okay, so let's see here. Okay, so the next topic here is finite state machines. So how can we build a finite state machine in Verilog? This is something that you very commonly will do in Verilog. It's very common. But the good news is that if you understand how to build finite state machines in logic, it's really straightforward to do it in Verilog. It's the same thing as we learned in last chapter. An FSM is comprised of 3 parts. There's clocked logic, which is the actual flip-flop that takes the next state and puts it into the current state on the clock edge. There's the next state logic, which is combinational, that computes the next state as a function of the current state and the inputs. And then there's the output logic, which in a Mealy machine is a function of just the current state, and in Mealy machine is a function of the current state and the inputs, and in a Moore machine it's just the current state, right? So you've got essentially, what does this mean? It's 3 always blocks. A finite state machine is 3 always blocks. One of them isn't always at flip-flop, and the other two are always at com, always underscore com. Combinational, C-O-M-B. OK, so here's an example. Got three states, S0, S1, S2. S0 is the reset. You can transition from S0 to S1 and from S1 to S2 and S2 to S0. And so we have this module here that says, oh, this is a divide by 3 finite state machine. So the purpose of this is to take a signal, take a clock, and divide it by 3. So you have your three always blocks. The first one is always at flip-flop, and it's very simple. It's sensitive on the clock and the reset. If you reset, you set the state to S0. Otherwise, you set the state to next state. So generally, this one is always the same. Now, in terms of this S0, this is an enumerated type. This is something else that's new. This is new in System Verilog. Verilog did not allow enumerated types. An enumerated type is where you create a type where you give it your own set of possible values that a variable declared of that type can have. So in this case, you're creating a type called state type, which can have value S0, S1, and S2. But notice that it still says that the syntax is kind of strange. And honestly, I would have to look this up because I wouldn't remember this off the top of my head. But it says type def enum logic 1 down to 0. You're saying you're telling the synthesizer this will end up being a 2-bit signal. And then you give it the 3 state values there. And then you give it a name state type. And then you declare state and next state are both that state type. And you have to put the 1:0 after that too, which seems redundant, but it's kind of strange. Like I said, I would have to look that up. I wouldn't remember that off the top of my head. In Verilog, you had to manually give binary values to each of your states, just like you do when you're designing a state machine by hand. But in VHDL, you use enumerated types for states, and now in System Verilog, you can use enumerated types for states. Everyone with me? So this clocked logic is pretty simple. It just controls the sequential part of this. The next state logic is always underscore com. They use a case statement, and a case statement is a very natural way to do next state logic, because that way you can have, for each one of the states in your case, you can put a separate block of code for each state. So this is like saying, if my current state is S0, then my next state is S1. Usually you're going to have if statements in here, though, too. So the reason why this looks so simple is because all of the transitions in this FSM are unconditional. There's no conditions. So if you go back to the graphic, there's no labels on these transitions. They're just unconditional. This thing is it's a divide by 3 counter, so I'm just constantly going in a circle. So you could put an if statement inside the case statement if you wanted to put conditions on these transitions. You guys with me? And then the output logic just says, in this case, it doesn't even use, it's so simple it doesn't even use an always block. It just says it uses an assignment, a concurrent assignment. Assign Q equals, and then if state equals 0, then Q is 1. Otherwise, it's going to be 0. Q is an output logic, by the way. Yeah, it's 1 bit. And oh, by the way, reset, I didn't point this out, but the reset state is state S0, and that's controlled up here in the clocked process. Make sense? OK, let me go ahead and let's try it out, see what this thing does. So I'm going to take this, copy it, divide by 3 FSM. OK, so I'm going to go back to here, cat to divide by 3 FSM dot System Verilog and I will paste, and then I will vlog, vlog divide by 3 FSM, it compiled. And I am going to open this up, by the way, in Vim, and then go over here to Model Sim. I'm going to go to Start Simulation, go to Work, click Divide by 3 FSM, and switch. This will switch my design over to the new one here. And it's working. It's going. Come on. Loading. All right, here we go. So I've got, let me kill this. Here we go. So here's the objects. I've got clock, reset, cue, state, next state. I'm going to go and say add these to my wave, which will put them in this little waveform viewer. You might be wondering why you have to do all this. Most designs have lots and lots of signals. Too many to have all in the waveform. Usually you only put the signals that you want to look at, that you're concerned with, or that you're using to debug in your waveform. I'm going to hit this little button down here that'll take the little prefix, the divide by 3 FSM prefix off, because I know where they're at. OK. All right, so I need a clock going, so I'm going to say force. I'm going to just, oh, sorry, force clock, rather. Clock. Tell Model Sim to get this thing going as a clock. And I am going to start reset off. I'm going to say force reset to 0, and I'm going to run. Run 500. What the hell? OK. So, oh, wait a minute. Sorry, I should have reset. Well, that's OK. What it's doing right now is it's working. See, it's going. Kind of strange it has S0 and S1 in there, though. But let's see what happens when we reset it. Let me say force reset to 1, and then run it. All right. So when reset went high, I stopped in its tracks, and state became S0, S0. I guess I must be doing that because they're two. Yeah, they're two. It's two. Is that because it's 2 bits? It's declared as 1 down to 0, I guess. Let me see if we could fix that. What happens if I just say state type here? Save it. Vlog. Divide by 3 FSM.v. Actually. What directory am I in? Yeah, I'm there. Did I misspell it? Oh, SV. Sorry, my fault. Forgot we're in System Verilog. There we go. All right, now let's restart and run. Let's see. Let's set up the clock again. So I'm going to hit up arrow until I get to the command. That's the clock command, and then force reset to 1. Run. All right, there we go. That looks better. There we go. So I guess that might have been a typo in the slide. Yeah, so there's 2 clock cycles, but because reset is asserted here, the state is stuck at S0. It's not going anywhere. It's ignoring the clock. The next state is S1, because anytime my current state is S0, my next state will be S1, because the next state logic doesn't care about reset or the clock. But it doesn't matter, because as long as the reset is high, I am not going to put the next state into the state. I'm not going to make the state the next state, right? I'm not going to do anything. I'm just going to sit here stuck. If I force reset to be, sorry, R reset spelled out, right? Reset to be 0. Notice, by the way, that I just happened to drop reset on the rising edge of the clock, right? Which meant that I'm not going to actually drop out of, go to my next state until a cycle later, because it's going to take an extra cycle. I released the reset on the rising edge, which is normally when it would go to the next state, but because I did it on the rising edge, it was too late. I had to wait until the next rising edge before I went to S1, right? All right, so if I run this, there it goes. So you can see the state is going S0, S1, S2, S0, S1, S2. So there's the state sequence. The next state is always, basically planning ahead to the next state, so it's always one ahead. So I got S0 here, S1 there. And my output logic is putting a pulse out whenever I'm in S0, which is not shown for whatever reason. They did not show that here. I don't know why. But in the output logic in the Verilog, you can see that Q is asserted whenever I'm in S0. And it's called a divide by 3 counter, or divide by 3 clock. And you can see that that's exactly what it's doing. The output, if you look at the period of the output, which is from rising edge to rising edge of the Q, it's comprised of 3 clock cycles of the original clock, right? Now, it doesn't have a 50% duty cycle, because there's no way to do that here with a divide by 3 clock, but it's a 1/3 duty cycle. But the frequency of my output Q is 1/3 of the frequency of my reference clock. So this is a divide by 3. This is dividing the clock by 3. It's reducing the frequency by a factor of 3. Any questions? Okay. Again, this design is, you could think of this as a template. Any state machine that you design in System Verilog should follow this as a template, because by doing that, you reduce the uncertainty of what you get when you synthesize it. Right? You're expecting this to synthesize to a canonical finite state machine type circuit, so you should use this this format. Now, some people will take the output logic and combine it with the next state logic, especially if you're doing a Mealy machine. That makes sense, right? So you could merge these two into one big always statement. That's okay, right? But you should have a state and next state signal and so forth. Okay. Any questions about that? Okay, so now we can build arbitrary. Now, by the way, it's not clear from looking at this because it's so simple, but think of the possibilities now. When you guys were doing these by hand, you were very limited because the next state logic was a truth table or a Carnot map that you had to build, whose inputs were all of the bits of the current state and all of the inputs. Well, how big can you make a truth table realistically on paper? 4 inputs, right? 4 input truth table would be a 16-row truth table, right? Maybe you could go to 6, maybe at most. I think when I was in school, we did some crazy, 64 6-input tables by hand. But you can't really go beyond that. And with a finite state machine, you're really limited because those inputs have to be both the current state and the inputs have to share all of those set of inputs, right? So what does that mean? That means that you can't really, realistically by hand, you're very, very limited on what kind of state machine you could design. But with this, you can make a huge state machine and then you just let the synthesizer worry about how to actually make it, right? Because it's all done in with Verilog, right? So you could put tons of states in here, you can have an arbitrary number of inputs and outputs, and you don't have to worry about the logic minimization or the wiring or the truth tables or the K-maps. It's all built in for you. All you have to do is describe the behavior here. Yes?
So whenever it assigns Q equal to state equals S0, so I see that like state equals S0, that's like just saying that it actually equals that.
Mm-hmm.
So how does that add it to Q?
How does it, I'm sorry?
How does that add it to Q? Wouldn't it just be like Q equals 1 if it is?
Yeah, I don't like this syntax. What it's doing is it's doing a conditional, and then it's relying on System Verilog's ability to take a conditional and resolve it to a logic, right? I don't like that. When I write code, conditionals are conditionals. They're either going to be in a ternary statement or an if statement. or a condition for a loop or something like that. But I would never assign, I would never do this because, for example, in C, think of, I don't know if you guys know this, but in the C, in Java you have bool. You have a Boolean type that is the type of a conditional expression like that, right? It's called a Boolean, true or false. Pascal had that, but C and C++, if you have a conditional like that, it evaluates to an integer. And false is a 0, and true is anything but 0, right? So in C, if you say A equals B, if that's true, it's not necessarily going to be a 1. I think it usually is, but it's not. According to the rules of C, it could be any value from negative 2.1 billion up to negative 1, and 1 up to 2.1 billion. All of those values are true. The only value that's false is a 0, right? So I don't like this idea of using a conditional and actually assigning it, mostly because I'm a C programmer, and to me that's heresy to do that, because there's no guarantee that this is going to, what they're doing is they're assuming that state equals 1 is going to evaluate to a 1, a logic bit 1, if that is true, but I don't like leaving that to chance. So I would have said state equals 1 question mark 1 colon 0, which would have made it explicit, right? Or I would have said always underscore com if state equals S2, then Q equals 1, else Q equals 0, right? So I would have made it a trinary or an if statement wrapped in an always block. I would have never done it like that. I don't like that, but that was how the textbook authors did it, or whoever wrote these slides for them.
And since it outputs a 1, if it is equal to S0, or I'm guessing it does that mean that there has to be something outside of that that actually adds that to Q, or keeps it instead of it being 1, it keeps adding it up?
Oh no, there's no adding. It's just a combination of logic that let me see. Where's the where's my waveform? Yeah, here we go. It's just a thing that just says whenever I'm in S0, I put that 1 out. If I'm in S1 or S2, I put a 0 out there. I assign a 0. There's no adding. The only thing that looks like it's adding, it looks like this is an accumulator sort of, but it's not. This is just the next state function is. It looks like it's an adder, because it's going 1, 2, 0, 1, 2, 0, 1, 2, 0. But it's not really an adder. This is the next state logic. It's kind of like an adder, but yeah, this. In other words, I think to more concisely answer your question, Q depends only on what is in state. So if that's S0, that's 1, and that's the only intelligence that the output logic has. That's all it's doing.
Okay, I was thinking whenever you say divide by 3, I was thinking it takes in some number or something like that, and then divides it by 3.
Oh no, don't get confused. When I say divide by 3, that's just the behavior that's what the circuit is logically doing. It's not explicitly dividing. There's no divide operator. In fact, there's no arithmetic in that thing at all. It's just a state machine that goes through a sequence of 3 states, but it's activated by a clock. And so in order to get through a sequence of 3 states, it takes 3 cycles, and thus if it goes through that sequence of 3 states periodically, regularly, every 3 cycles, asserts this every 3rd cycle, then it naturally becomes a divide by 3 counter. But there's no explicit divide happening. It's just all in the behavior of it, what it's doing, right? Yeah, there's no actual arithmetic.